So we have now taken a look at derivatives, and we've defined them using a limit definition of a derivative, and we've done some calculations of finding the derivative of a function. And what we started to notice is the algebra involved in calculating these derivatives using the limits can get pretty complicated pretty quickly. So what we want to be able to do is see if we can come up with some rules that are going to shorten up that process of finding a derivative for us. So that's what this is going to be about, finding some basic differentiation rules. So the first one we're going to talk about is the constant rule. And the constant rule says that d dx of c equals 0. And if you remember, we discussed the fact that we are going to start to kind of mix up some of this notation. So remember what this says. d dx means you're about to take the derivative of c, and that's the derivative with respect to x. So when you take the derivative with respect to x of c, you get 0. Well, because this derivative is with respect to x, that means c represents a constant. So this says the derivative of any constant is going to be 0. That's the constant rule. This is all assuming that c is a real number. If c is imaginary, we have to rethink it a little bit. But for now, we're just going to deal with real numbers. So the derivative of any constant that's real is 0. So there's a geometric argument or a graphical argument to support this. If you take a look at the graph of any constant function, what does the graph of a constant function look like? Well, it should be a horizontal line. The horizontal line, y equals c. Whatever that constant is, y will be equal to it. So when you talk about the derivative of this constant function, if you're looking at its graph, you're talking about the slope of its tangent lines. Well, if you start looking at the tangent lines, it doesn't matter which x value you're looking at. The tangent line to a constant function is always going to be horizontal. And what's the slope of every horizontal number? Well, it's 0. So that's why the derivative of any constant is going to be 0. So that's the geometric argument. There's a much more rigorous argument for it. So here's the mathematical proof of it. If you let f of x equal c, and again, you can tell c is a constant because we have said f of x. That indicates that x is my variable. So there is no x on this side. It's a constant function. Then the derivative of f at x, which is, here's your limit definition that we've been discussing. It's the limit as h approaches 0 of f of x plus h minus f of x all over h. When you go to calculate this derivative, what is f of x plus h for a constant function? Well, the constant function is constant, so it's c. That's where the c comes from. What is f of x for the constant function? Also c. So in other words, your numerator becomes c minus c, also known as 0. So what you're taking is the limit as h approaches 0 of 0 divided by h. Well, that's the limit of a constant, which is the constant. So that's the mathematical proof. When we use the constant rule, we find things like the derivative of 5 is 0. No surprise. The derivative with respect to x of e is 0. Here I intend e to be the e that you're used to when you're looking at natural bases of exponentials or logarithms, that 2-point something number. But even though it's written as e, e represents a specific number. So its derivative with respect to x is going to be 0. The derivative with respect to x of a. Notice I didn't tell you what a is, but as soon as you see that this derivative is with respect to x, a is a constant, so its derivative will be 0. So that's the constant rule. The power rule is the next one we're going to make lots of use of. The power rule says the following. If f of x equals x to the n, so let's look at that for a second. F of x, that means my variable is x, which makes n a constant. So this is x raised to some power, and according to the last few words in this, this rule applies for all real n. So that exponent has to be real. then the derivative of f with respect to x is going to be n times x raised to the n minus 1. In other words, the exponent drops down in front and is written as a coefficient, and then x is raised to a new power, and that new power is exactly one less than the power it started with. Let's take a look at an example. So if you have f of x equals x cubed, then the derivative of f of x is 3, take the exponent and drop it down as a coefficient, times x raised to the new power, which is 1 less than 3, also known as 2. So the derivative of x cubed is 3x squared. For f of x equals x, remember that is technically x to the first power. So if I put in an intermediate step, I would drop 1 as a coefficient. I would have x to the new power of 1 minus 1, also known as 0. But what is x raised to the 0 power? Well, that's just 1. So this becomes 1 times 1, also known as 1. So the derivative of x is 1. If you have f of x equals 1 over x squared, now we don't technically at this point know how to take the derivative of a function that contains a ratio. But what you can do is you can rewrite this as f of x equals x to the negative 2. That's using the exponential rule that says if you have a raised to the negative m, that's the same thing as 1 over a raised to the positive m. I've actually just used it in the reverse order. So instead of writing this as 1 over x squared, we can write it as x raised to the negative 2 power, and then apply the power rule. Drop the negative 2 in front as a coefficient, times x raised to the negative 2 minus 1, which is negative 3. So the derivative of 1 over x squared is negative 2 over x cubed, or negative 2 times x to the negative 3. For f of x equals the square root of x, again, we don't really know how to take a derivative of a function that involves a radical. So what we want to do is rewrite that radical in a way that's going to allow us to apply the power rule. What you have to keep in mind is this little rule right here. In general, when you have something raised to the m divided by n, so that's a fraction in your exponent, that is the same thing as the nth root of a raised to the m. It's also the same thing as the nth root of a with the m on the outside of the parentheses. These are interchangeable. Traditionally, we're probably going to use this one a little bit more. It saves us some simplification along the way. But this is the relationship between fractions and exponents and radicals. So when you see f of x equals the square root of x, keep in mind x is being raised to the first power under there. The implied index, if there's none written there, is 2. So if you apply this rule, that says that the square root of x is the same thing as having x raised to the 1 divided by 2 power, or 1/2 power. Once you rewrite, you're able to say then that the derivative, according to the power rule, should be 1/2 times x raised to the 1/2 minus 1, which is negative 1/2. Well, that's the same thing as 1 over 2 times the square root of x. So that's the power rule.